Hi guys, in this lecture we will look into the proportional plus derivative feedback controller. Essentially, it's a proportional plus derivative controller with a slight tweak that allows us to obtain great improvements. Proportional derivative feedback control allows us to remove the overshoot that we saw in the last lecture. Effectively, it removes the zero from the transfer function. Let's now have a look at proportional plus derivative feedback control through its typical block diagram. We start with our typical reference signal RT. Now, usually we actually subtract the output of the system to RT to get our error. But now we do something slightly different. So the output of the system y'(t) is actually fed back to RT through two branches. The first one passes through the derivative gain kd and the differential d over dt, so we multiply it by s, exactly like in a proportional plus derivative control, but now that derivative part of the system, instead of being in the controller, is actually in the feedback. We also have another branch which is just the output signal y'(t) on its own with no calculations applied to it. So we do the sum of these two branches and then we feed that back to the reference signal to get the actual error e'(t). So as usual, we have our proportional gain in the controller, which is Kp. We pass the whole error through that proportional gain to eventually get a control signal ut equals Kp et, which you will all recognize as the proportional part of the control signal, minus Kp Kd multiplied by the differential with respect to time of yt. Okay, so Kp Kd dy dt actually comes from the feedback of our system, and that is why the derivative gain Kd is actually multiplied by the proportional gain Kp. So we feed this control signal back into our plant and we eventually get our output signal y'(t), which is then again fed back into the error signal, and so on and so on. So here, our control transfer function GCS is equal to Kp only, like in a proportional control loop. However, we also have a feedback transfer function, which is a transfer function between y'(t), the output, and the error e'(t), and it is equal to 1 plus kds. So you will recognize kds as the derivative control part, while the 1 represents the untouched output of the other branch of the feedback. Let's have a look at the structure of our system. So we have the error signal e'(s), and it is equal to Rs, the input signal, minus Hs, the transfer function for the feedback, multiplied by the output y'(s). But we also know that y'(s), the output, is equal to the controller transfer function multiplied by the plant transfer function multiplied by the error. So GCS times GPS times e'(s). So we can actually write that y'(s), the output, is equal to GCS times GPS multiplied by the error, which is Rs minus Hs times y'(s). We develop all that and we can get the transfer function for our whole system, that is y'(s) divided by Rs. So it links the output of the system to the input of the system, and it is equal to Kp GPS divided by 1 plus GPS multiplied by Kp plus Kp KDS. Let's go back to our DC motor model that we used in the previous lecture. Again, we have the plant function GPS equals 699 divided by S multiplied by S plus 1.95. We want a critically damped control with a settling time of 0.4 seconds. The first thing we want to do is look at the characteristic equation of our system. As usual, we can extract it from the transfer function of the system by equating the denominator to 0. And in this case, it is 1 plus GPS multiplied by Kp plus Kp KDS equals 0. So we're filling the numbers with what we have from our example, and we get that the transfer function is s squared plus 699 kpkd plus 1.95 s plus 699 kp divided by s multiplied by s plus 1.95 equals 0. If we want this fraction to be equal to 0, its numerator needs to be equal to 0. So s squared plus 699 kpkd plus 1.95 s plus 699 kp equals 0. Using our typical characteristic equation for second order systems, which is s squared plus 2s multiplied by a damping coefficient multiplied by omega n, the natural frequency of the system, plus omega n squared equals 0. We want a critically damped system, so a damping coefficient of 1. And we also know that the settling time Ts is equal to 4 divided by omega n. In this case, we want a settling time of 0.4 seconds, so we get omega n equals 10 radians per second. Filling in all the numbers, we can now equate the actual characteristic equation of our system to the characteristic equation we desire with respect to the performance we want, and we get that the proportional gain Kp is equal to 0.143 and the derivative gain Kd is equal to 20 minus 1.95 over 699 Kp, so 0.1805. The transfer function of the system actually now becomes y apostrophe s divided by rs equals 100 divided by s squared plus 20s plus 100. So for the exact same planned transfer function as our previous lecture, we actually got a transfer function that has no s in the numerator, so no 0. And we did this by using a very similar method, the only difference being that the derivative term, instead of being in the controller, is in the feedback of the system. And as you can see to the step response, we got a really nice response without any overshoot. And overshoots can be okay in some cases, but they can also be very, very important in other design projects. That means you really want to get rid of them. In this case, using proportional plus derivative feedback is obviously very interesting. In the end, what are the advantages of proportional plus derivative control? First of all, it improves damping, and this leads to very nice responses with a lot less oscillations. It also increases the degree of stability of the system, and this is due to the larger damping. It removes the need for mechanical dampers because now the control system is actively damping the system. And in the case of proportional plus derivative feedback control, it does not introduce an additional 0 in the closed loop transfer function. As we saw in the previous lecture, proportional plus derivative control on its own can sometimes, not always, but sometimes introduce an additional 0 in the closed loop transfer function. Obviously, it has its disadvantages. First of all, it does not necessarily lead to a steady state error of 0. As we saw previously, for this we actually need to add integral control to our controller. The noise in the feedback sensors can be amplified by the derivative term of the control system. Why? Because noise is essentially extremely fast variations up and down at random. And because derivative control actually takes the rate of change of the signal, noise has a humongous rate of change, and this actually can be detected by the derivative term and largely amplified. Sometimes, as with integrals, the implementation of differentiation can be very complicated, but this will all depend on your system. So this is it for proportional plus derivative control. I hope you guys enjoyed it. If you have any questions, as usual, please do not hesitate to message me. Thank you very much, guys.